brief introduction about you and your company. This advanced functional printer we have downstairs is from like a company from Switzerland, Norbert Schlafli, NSM, and now we are delighted to have Micheal Schlafli, who is the CEO of this company. NSM is a leading global provider of high-precision printing systems for industries from semiconductor to photovoltaics and to printed electronics, and also advanced packaging. And also, I should apologize that we should skip this tour. We should. One, two, three. Yeah, okay. We skipped the tour of this machine because we have been behind the schedule. So we just postponed it after the last speaker we have around 4:30. We can walk there and see the machine. But as introduction, with nearly 40 years of innovation and industrial impact, NSM company has become a trusted partner for both large-scale manufacturing and cutting-edge research. And Micheal has been CEO of NSM since 1995, guiding the company's journey for expansion and technological leadership. And over the past 3 decades, he has played a central role in bridging industrial printing solution with R&D communities worldwide. Thank you, Micheal, for being with us, and we can start. Thank you so much.
Thank you very much, Naime, for the nice introduction. So I would like to share then my screen. Huh? So can you see my screen?
Yes.
Okay.
Yes, all good.
Oh, good. Just let me. So yes, good afternoon and thank you for the invitation. Thank you, Mainak and Naime, for hosting this workshop. My name is, as you heard, Micheal Schlafli from NSM in Switzerland. Today, I will introduce the Challenger 650, a modular high-precision platform for printed electronics. NSM was founded in 1985 in Switzerland. We are based in Zofingen, that's between Zurich and Bern. Since then, we have installed more than 400 systems worldwide. We design and build customized machinery for research, for laboratories, and for pilot production. Our portfolio ranges from a compact benchtop system to fully automated roll-to-roll and sheet-based lines. These systems are used in applications such as solar cells, batteries, sensors, carbon captures, actuators, and many others. Evolution of printing at NSM. In the 1990s, NSM developed lab-scale printing and coating systems, mainly for the graphic and chemical industries. In the 2000s, we moved into functional printing through our first EU research project. That's a picture here from a roll-to-roll printing machine we built in this project. Today, we provide custom-built high-precision platforms for research, development, and pilot production. Since then, we have continuously developed modular platforms for both traditional printing and functional applications. This is the Challenger 650, our modular high-precision platform. It combines printing, coating, laminating, and drying in one system. Modules are integrated to customer needs. It comes with a camera alignment system. Positioning repeatability is about plus minus microns. The platform handles rigid and flexible substrate up to 300 by 300 millimeter and a thickness of about up to 4 millimeter. Processes are recipe-based and automated. The process speed goes up to 90 meters per minute, depending on the module and the ink. Now let me show you what this modularity really means. Here you see the process modules that can be integrated into the system. We support many technologies such as slot die, inkjet, screen, flexo, rotogravure, gravure offset, lamination, substrate pre-treatment such as Corona, and then different drying and curing. And most importantly, the platform is open for additional modules as needed. EMPA in Switzerland validated the Challenger 650. This diagram here shows that most markers are within plus minus 5 micrometers. That demonstrates high accuracy and repeatability of the system. Next is a short demo video of the Challenger 650 in operation. Here you see the vacuum substrate chuck, which is moving here under the Corona treatment. Then it moves to a flatbed screen process where we printed, in that case, a graphene-based ink. And then we see here a flexo print with nanosilver ink, followed by a near curing process. Then the chuck goes back that we can check the printed register mark and the accuracy. That shows a gravure offset print. It's an indirect print. Then a conventional gravure. We have also a lamination station. You see here how two substrates are laminated together. Then we can integrate the slot die coating stations for applying thin film layers. We integrate inkjet bridge. Depending on the application, we can choose inkjet heads from several suppliers. And at the end of the machine, we have different curing stations like photonic sintering, hot air dryers, UV curing, and near dryers. Now let me show you the exact configuration installed to the protoprint at Monash. So here, that's the configuration of the machine which is on your side. We start here with the substrate loading. At the same position is also the camera alignment. Then we have integrated the flatbed screen unit. Then we have an empty space where you can integrate a second flatbed screen unit or another technology in future. Then we have, it's called the combo unit, because with this unit we can do either flexo, gravure, gravure offset, or lamination. Then there is a space, another empty space, for example, for another combo unit. After that is the radiation shutter, which blocks the stray light, so the ink doesn't dry inside the print unit. From the dryers here, we have integrated a near curing unit and a UV curing station. This setup supports research on materials and 2D printed devices, and it also enables collaboration between academia and industry. Now let's have a look to the dimensions. The machine is 6.7 meters in length, 1.5 meter in width, and 1.85 meter high. This slide shows the mechanical platform. It is built from 2-meter structure elements. At each interface, the elements are precisely aligned and rigidly linked. The concept is scalable from a very compact setup to a 12-meter long multi-module line, depending on the customer's configuration. Using the 2-meter modules also ensures good access to typical labs. Now let's look at the camera alignment station, the first station on the machine, together with the loading station. It aligns the substrate for accurate layer registration. The camera system is adjustable in height and in X and Y position. We have here different adjustment possibility that you can move with the cameras up and down, but also in all directions. When you have printed marks which are on other positions, it's important that you can move with the cameras. Next, the flatbed screen unit. Movements in X, Y, and Z are controlled by linear guides and servo motors. The flute bar spreads the ink across the screen, and the squeegee here pushes the ink through the mesh onto the substrate. We have a force adjustment for fine-tunes the squeegee presser. This is the combo printing unit. In a single station, we can run 4 processes: rotogravure, flexo, gravure offset, and lamination on the same base. We only have to exchange the rollers and the doctor blade, and then we can do either the one or the other. All axis adjustments are software controlled, servo-driven X, Y, and Z, and in micrometer steps. We can do all adjustments in 1 micrometer steps. The camera detects the 0 position on the printing cylinder. This enables micrometer accurate multi-layer printing. This slide shows the gravure and flexo setup in the combo unit. Both processes can be run with an open doctor blade. With only 2 milliliters of ink, we can make several test prints. That could be quite important when you use expensive inks. Or we use a closed chamber doctor blade for longer runs without refilling. In gravure, the gravure cylinder prints directly to the substrate. That's the gravure setup. And by flexo, we have an Anilox roller. It's also the inking roller, which transfers a defined amount of ink to the plate cylinder with either a sleeve or a polymer plate, and then transfers the structure to the substrate on the vacuum chuck. Here you see 2 more configurations of the combo printing unit. On the left side, it's indirect gravure, also called gravure offset. Ink is transferred from the gravure cylinder to the rubber cylinder, and then from the rubber cylinder to the substrate. Here, there is a laser pointer. On the right is the lamination. We use a perforated lamination cylinder. You see here the hose with switchable vacuum. So now I will play a short video that shows the lamination process. You see here we have a pre-structured substrate on the vacuum chuck, which is moving to the lamination unit. And now the vacuum goes off on the substrate chuck and on the cylinder. That's how we transfer the substrate to the lamination cylinder. See here the air hose. Then it goes back to the loading station again. And then we have another pre-printed substrate already on the chuck. And this is just to demonstrate the precision of the lamination unit, also the repeatability precision. It's a dry lamination here just to demonstrate the high accuracy. We lay down just two pre-printed substrate on top of each other, and we focus now with the cameras the alignment marks, and you see here the field of view is 1 by 1 millimeter, and then you can imagine how precisely these two substrates lay on top of each other. So lamination is also often used in printed electronics for example, for encapsulation, which is quite important. This slide shows then the end of the machine with the drying stations. So we can integrate, as we saw in the video, hot air dryers, near curing, UV, and pulsed flash curing stations. On your system, there is a near curing and a UV lamp integrated. This shows the control interface. It is a PC-based with a recipe management system. We define complete process sequences, and all module parameters are stored and recalled. Sequences can include many steps and repetitions. Once the substrate is loaded, the sequences run fully automatically until the unloading station. On the next slides, you will see a few impressions from the installation at 2D Protoprint at Monash University. So this picture shows my colleague, Rolf Meyerhans, our CTO. You can see the many cables, boxes, and connections. So it gives an impression of the complexity also of the whole system. Here you can see the 2D Protoprint team together with the NSM technician during the commissioning and training. The 650 here in the back and the control desk in front. And now I want to show you some customer applications with the Challenger 650. The next 6 slides are from our customers. This was a collaboration project between EMPA and Folex, who provided the transfer film. Their graphene ink was flatbed screen printed onto a Folex transfer film on the Challenger 650 at EMPA, then heat transferred to fabric. The long lines are conductivity test tracks, this one here, and the interdigitated patterns are sensor electrodes. This slide shows printed transistors from EMPA. The source, drain, and gate electrodes were all flexo printed on the Challenger 650. The semiconductor and the dielectric were added by aerosol jet printing on a separate system. Next, EMPA project on stretchable transducers. The PDMS layers were plate coated and the electrode material were flexo printed on the Challenger 650. From these coated films, modules were cut and stacked to build the devices. Each transducer consists of 400 layers. So here we have 400 layers, and this is about 20 millimeters height. The project later led to EMPA spin-off company CT Systems, which was acquired by Detweiler in 2022. As another example from EMPA, here we see work on flexible CIGS solar cells. The grids were gravure printed with a line width of about 80 micron heights and 80 micron width, sorry, and a height of 1 to 2 microns. After printing, the lines were dried in an oven and then flash annealed to improve conductivity. In the end, the conductivity reached about 20% of bulk silver, limited by crystal structure and porosity. Here we see a project at the National Research Council in Ottawa, Canada, also using the Challenger 650. For the organic solar cells, the transparent interlayer zinc oxide was slot die coated, and the organic semiconductor, the red layer here, was gravure printed, and the TFT electrodes were flexo printed. This slide shows a project from our partners at ITA, Leibniz University in Hanover, Germany. All these results are also achieved using the Challenger with flexographic printing of polymer optical waveguides. On the top left, you see an optical waveguide directly printed on a PMMA substrate. It was built up in 15 layers of UV polymer using flexographic kiss printing. Thanks to the precise control of the Challenger 650, the printing height can be adjusted in 1 micrometer steps via software, layer by layer, if needed. That means each new layer makes contact only with the previous printed layer, but not with the substrate. On top right here, you see optical waveguide used as data transmission path. We can see it here, this one and this one. Here the data is transmitted bidirectionally over 2 PMMA-based waveguides, a quasi-Ethernet link. At the bottom left, thermoformed PMMA waveguides with couplers to other waveguides for low-cost optical bus systems.
Excuse me, Michael, to interrupting you. It's just 2 minutes remain for your time.
2 minutes, it's okay.
Yeah.
Oh, then I
Okay.
have to.
Yeah.
Okay. Oh, at the bottom, then finally, the bottom right, you see an electrode optical circuit board. The optical waveguide is integrated into the PCB as a multi-layer stack. Printed UV polymer cladding provides smooth surface for total internal reflection. The central stripes here is the waveguide core. These slides show how NSM is well integrated into the Swiss community, in the Swiss research community. Within Scalar, our task was to retrofit the gravure unit on the Challenger 650 at EMPA and adapt the control software to print with microstructured shim sleeves. We also implemented force control doctoring and printing pressure, and we developed a doctor blade unit with interchangeable inserts for different angles. These features are essential to print microstructures only a few micrometers wide. Dr. Jakob Heyer from EMPA will present Scalar in more detail later today in the program. These examples show what our partners have already achieved on the 650. And I think tomorrow during the hands-on workshop, you will see further device demonstrations produced on the NSM printer here at Monash. Now, our latest developments at NSM. The first of these developments is the Explorer 800. This is a roll-to-roll inkjet printer. It is designed for functional applications. The system works with a 630 millimeter webbits and the precise web handling. It supports up to 4 industrial print heads. The drying is modular. We can integrate hot air, near, UV, or photonic curing. The platforms supports material testing and also pilot production. The first 2 systems have been delivered this year. The second one is Explorer 801, our roll-to-roll coater for perovskite solar cells. Several slot die coating stations and drying modules can be integrated. Atmosphere control is built in. It coats thin layers up to 300 millimeter wide. This makes the solar coater highly flexible for both research and pilot scale production. Also here we just on the end assembling, the machine will be delivered to a customer end of November. Looking ahead, we are working on several future developments for the 650 platforms. Currently, the largest substrate size is 300 by 300 millimeter. We are evaluating larger substrates carrier for fuel cells components and other large panels. We also plan additional process integration, such as inline quality inspection and environmental options like air filtration, automated substrate alignment, and the substrate handling system. This shows that the 650 is modular today and will keep evolving with new research needs. That's the end of my presentation. Thank you very much for your attention. I look forward to your questions.
Thank you very much, Micheal. Indeed, it was very good introduction to this machine that we are going to have a tour this afternoon and also hands-on workshop around that tomorrow. And I'm also appreciate you for being always supporting for technical issues, and we are dedicated ourselves more than previous to explore more with printability of different kind of materials with this machine. Thank you very much. So just time for one quick question, if there is in room. Kelvin, of course, is a PhD student working with this machine.
Oh.
Yeah. So I have a quick question that when, in my printing, I need to use a lot of high boiling point solvent, which is very hard for drying. And I see that properly IR drying is not strong enough to completely dry the sample. Do you recommend any other function, or have you evaluated any way of drying of high boiling point solvent for printing before using this printer?
So your question is that you have ink, you have a layer on a substrate, and the drying
ink with high boiling point solvent. Yeah.
Yeah, and you use the near dryer, and it's not totally dried. Did I understand?
Yeah, exactly.
That?
Exactly. Yeah.
What many of our customers do, they just go for a second turn to the dryer.
Yeah, it's a kind of compromise between complete drying and also sometimes flexible substrate, which are polymer, are affecting, but too much heating the substrate, right? We should find the optimum condition. So I got your answer in that way, right? Because when you are increasing the different the times that we are going for drying, sometimes, for example, PET is damaging by heating if it's near IR drying, right?
Yep.
Curing.
Yeah.
So it's a kind of compromise. Maybe we can tune more parameters with software. This is his question.
Are you want with the same dryer, with the Adfos near dryer to modify the software? We would have to check what is possible. Yeah.
Yeah. Thank you. We will stay in touch.
Yes, please. Yeah.
Any question online? Okay. Once again, thank you very much, Micheal. Thank you.
Thank you, and have a great workshop. Thank you very much for
Thank you
inviting us.
very much.
Thank you.